Hello, bonjour, guten tag, ciao, buenos dias, boa tarde, ni hao, dzień dobry, privyet, and good day, mate. I believe those greetings cover about 95% of the pre-registered webinar audience. I'd like to apologize for my poor pronunciation of some of the greetings, but I would like to thank all of you around the globe for joining us on this webinar. My name is Timothy Gotzik, and I look forward to telling you about how LUX technology enables better flexo print. First, I'd like to talk a little bit about printing technology in general. When package buyers are selecting a method for printing their packaging, they have a choice of a number of different technologies, and we try to keep this in mind when we're designing our research efforts to improve flexography. In particular, as you look at how the different technologies stack up in terms of quality and cost, which are usually foremost in buyers' minds, this is how we see them. Digital is a little bit unique, so I have it separated out because its quality and cost differ depending upon the application and the run length. But when you look at the quality rankings of the others, typically flexography falls somewhere below that of gravure and offset, who are regarded as having the highest resolution and greatest quality of all the print technologies. In comparison, when you look at cost, again, digital stands somewhat separate because it's so dependent on run length. But here, flexography has a much better profile and often is considered to have the lowest cost of any of the package printing technologies. The obvious comparison here is that if we could find a way to make flexography have a quality that was equal to or better than gravure and offset, we would have a very competitive technology. And fundamentally, if we had equal quality combined with a lower cost, this would end up in more packaging being printed by flexo, which is of interest to virtually everyone listening to this call. Now, let's talk a little bit more about print. Print is a two-dimensional medium. And so when you're looking at a package or anything that's printed with a halftone image, you're looking at a print that is created by the position, the color, and the size of little dots that are overlapping one another. But it's fundamentally a two-dimensional problem that you have to solve. As long as you have the right size of dots, the right color, and they're in the right places, you'll get the right image. We use screening to address these two-dimensional issues, where in the conversion of a continuous tone image like that found in nature to a halftone image like that used to print on a package, you go through a raster image processor, commonly known as a RIP, in order to create that. There are a number of different algorithms that are used to determine the placement and size of the dots. They range from very simple ones like AM screening to much more sophisticated screenings that have been developed in recent years. But fundamentally, this is a software issue, determining the size and position of the dots. However, when you look at a flexographic plate, you're not confronted with just a two-dimensional problem. The dots have size and position in the XY plane, but they also have a third dimension, height, which means that the shape of the structure underneath the top of the dot is important as well. Now, addressing this third dimension is really what comes into play when we make a plate. In moving from a file to a relief plate, there are three places where we can have an impact on the dot shape. The first is during the image transfer to the mask or ablation step, with the laser type that's used and the resolution or spot size of the laser can change can make the hole in the mask different, and that can influence the dot shape. The second stage is during the image transfer to the photopolymer or UV exposure step. Here, the chemistry of the plate fundamentally can change the shape of the dot somewhat, and also the UV exposure nature, its collimation, its wavelength, its intensity, things like that can have a pretty large effect on the shape of the dot that results. Also, there's a little bit of an effect from the processing step where, depending upon whether you're using a solvent or thermal processing of this plate, you can create slightly different dot shapes. But fundamentally, in comparison to the screening issue, the third dimension that we're dealing with here is determined by hardware, which is really what determines the shape of the dots. We believe that flexo is all about the dot, and that really the interaction of that three-dimensional plate dot with the two-dimensional substrate is where the magic and mystery happen. The three images that are shown on this slide really capture the entire value creation mechanism of flexography, which consists of the three relatively simple but rapidly occurring steps of deposition of the ink on the top of the dot, the contacting of the ink dot with the substrate, and the release of ink from the top of that dot onto the substrate. Fundamentally, this is where everything happens, and we believe that if you make the right dot on the plate, then the best print will follow. This begs the question of what is the right dot? Well, there's a simplistic answer to it, but and I'll give it to you, but it helps to explain the perspective that we take on developing the right dot, which is that fundamentally the right dot is the one that gives you the print you want. And so instead of just making dots and arguing over their structural characteristics, we always are sure to print all the dots we make to understand exactly what their impact is on the final product, because at the end of the day, a dot is just a way of making a print. This is an example of the kinds of dots that we can make, and this is just a subset of hundreds that we've been able to make over the last several years. These are all actually made on the same photopolymer, so it shows that it's possible to get a wide diversity of different dot shapes, even out of the same chemistry. We have printed all those dots and more, and I can say that from our experience, we found that there are lots of dots that do work, but some dots work better. And there are 4 factors that we believe are most important for making a good printing dot. The first is dot surface morphology, which is just a fancy way of saying the shape of the top of the dot. It can be flat, as shown in this picture, or it can be rounded, or it can be anything in between. The edge definition is also important. The edge is essentially the definition between the printing surface of the dot and the support structure or side of the dot. And once you're able to define those as 2 separate areas of the dot, you can independently optimize the 2 and make each perform its function best. The third is the valley depth. The valley depth is the depth between the top of the dot and the bottom of the valley in between it and the dot next to it. This is very different from the relief of the plate. The relief of the plate is determined by the height of a solid to the floor of the plate, which, for instance, in a digital plate might be 20 mils. The valley depth in a process area between 2 dots is usually much shallower. It can often be only 1 or 2 mils deep. Having a deeper valley depth, we believe, prevents interaction of one dot with the one next to it and leaves a little extra room for ink to accumulate if the plate is being slightly over-inked. The fourth factor that we believe is important is the shoulder angle, which is the angle between the dot surface and the supporting shoulder. As with the edge definition, this is essentially a measure of how separate the two portions of the dot, the print surface and the support structure, are, and again allows you to optimize the 2 independently. In recent years, there's come to be a lot of argument about what is the right dot, and the 2 that have emerged, general classes of dots that are being discussed a great deal these days, are essentially the round-tipped and flat-top dot that you see presented on the screen. Let's talk a little bit about what's different between these 2 dots, and then I'll show you some of the ways that they differ in performance. On the left, you see the typical standard digital plate round-tip dot, and on the right, you see a flat-top dot. And both of these can be produced by a digital workflow, which is, of course, very important since most people have gone to digital workflows for its efficiency and ease of modification. An interesting difference between these 2 is the fact that the dot height of the standard digital dot is actually slightly below that of a solid in the same plate. This is due to the effects of oxygen, which tend to recess the smallest dots slightly compared to the solids. In contrast, the flat-top dot, even at its very smallest size, has a height that is what we describe as type high, meaning that the smallest dot top is exactly the same height as the solid within the same plate. So all of the surfaces are at equivalent height in a flat-top dot plate. As far as mechanical stability goes, obviously standard digital dots are more than stable enough, as millions and millions of feet have been printed with them. However, everyone knows that they're also prone to becoming unstable, particularly in the smallest highlights, if they're not properly formed or if you don't get the bump curve right. I'll talk a lot more about the bump curve in coming slides. For flat-top dots, they're inherently somewhat more stable because they have a broader base and they have a better support structure than the standard digital dot. I'll show you some pictures in a bit that give you an idea of exactly how great this difference can be. And then finally, the mask-to-plate imaging between the 2 dot types is considerably different. Because of oxygen inhibition that I mentioned before, the standard digital dot requires an adjustment factor, usually called a bump curve, to compensate for the oxygen inhibition. This allows you to actually form the smallest dot that you want, but in order to do it, you kind of have to put a fudge factor into the mask to make it work. In contrast, the flat-top dot has a 1-to-1 reproduction profile, which means that whatever size hole you burn in the mask, you will get the same size dot in the photopolymer. This takes away the issue of the bump curve entirely. We have a solution that we believe delivers flat-top dots in a high-quality manner and fundamentally enables higher quality